Taking a look at CBE 360, it's an expert from Marley's textbook. Chapter 5 is titled Typical Process Systems. This chapter is around 40 pages long. Section 1 is the introduction. The text starts as, examples in the previous two chapters have demonstrated that physical systems, which involve very different physical principles, can have a similar dynamic behavior. The concept that a single model type can apply to a wide range of entities in process plants and biological units and economic communities and so forth provides the basis for system analysis. Thus, it is possible to acquire understanding of a large number of systems from a thorough study of a much smaller number of basic models. In this chapter, we study some fundamental model structures that occur frequently in process plants, along with their effects on dynamic behavior. This experience will enable us to recognize the effects of process design on dynamic behavior. First, the behavior of some simple basic systems, such as first and second order and dead time systems, is summarized using the results from previous chapters, and we have extensions. So secondly, the behavior of these simple systems and series structures is determined. And then third, the behavior of parallel structures of simple systems is introduced. So we'll have first and second order and dead time systems encapsulating series and parallel. And then fourth, the effect of recycled structures on dynamic responses are demonstrated. And this chapter concludes with an investigation of more complex physical systems of special importance in the process industries. So we have staged systems and multi-input, multiple output systems. In these sections, the manner in which the behavior of simple systems is altered by common process structures is derived for simple idealized models, but is demonstrated for important process examples involving levels, heat exchangers, chemical reactors, and distillation towers. And this coverage demonstrates that the engineer must master both the physical principles of specific processes and systems analysis techniques to determine the dynamics of chemical process quantities. Section 2 is titled The Basic System Elements. The text starts as, the coverage of process dynamics begins with the simplest elements, which are often encountered and combined to model more complex systems. Since examples of most of the elements were introduced and included in previous chapters, the coverage is concise here. The basic model structure for each element is first defined, and several physical examples are given, with the system input designated by X and the output as Y. The chemical process principles should be apparent to the reader, while the electrical and mechanical models are based off Kirchhoff's and Newton's laws, and the reader is referred to Ogata and Weber for derivations. The graphical and analytical results for common inputs for several basic systems are summarized in Figure 1. The presentation of results in such a figure seems to have originated with Buckley. Only the amplitude ratio is present here, because more extensive frequency response analysis, we have a process, we have a mixing, we have under damped reactor, we have plug flow, and then we have a tank with an inlet and outlet. We're given the step response. We're given the step response, and there's a graph for the output versus time. Likewise, we're given the impulse response, and then we're given the sign response. And sign response is with log of the amplitude ratio versus the log of the frequency. So, in the introduction, we introduced that we'll be talking about first order and second order and dead time systems. Here we're presenting first order system. The first order system occurs as a result of a material balance or energy balance on a lumped system. It's demonstrated in example 3. It's demonstrated in example 3.1 and 3.6, and some further examples are given in figure 5.2. The differential equation and transfer function for a first order system is given as equation 5.1. Here we have a differential equation. It's first order, so we have tau times the differential of the output variable with respect to time plus the output variable with respect to time, and this is equal to the proportional gain times the input variable with respect to time. We're also given information on the transfer function. As discussed previously, the transfer function is the output over the input. As discussed previously, the transfer function is given as the output over the input, and this is written explicitly in variable Laplace domain. And then for a first order system, it's simply the proportional gain over tau s plus 1. And the step response is monotonic with its maximum slope at the time of the step, and the time to reach 63.2% of its final change is one time constant. The final steady state change is equal to the proportional gain times the change in the input variable. Here we have equation 5.2, it's called the step response, and the step response is given as equation 5.2. It's given as a differential variable of the output variable with respect to t, and we're saying that this is equal to the proportional gain times the change of the input variable, and then this is multiplied by 1 minus the exponential of negative t over tau. So, as we said before, the final steady state change is equal to proportional gain times the change in the input. So, this would be the differential variable of the output variable with respect to t is equal to the final steady state change multiplied by an expression 1 minus exponential to raise to the power negative t over tau. An impulse input occurs over a negligible time and transfers a finite amount into the system. For example, rapidly introducing a small amount of tracer into a stirred tank emulates a perfect impulse. The impulse response shows an immediate increase at the time of the impulse, which for a idealized stirred tank example would mean that the concentration would change instantly by mass of tracer per unit volume. After the impulse, which is denoted as c, the system follows an exponential path in return to its final condition. Equation 5.3 is termed the impulse response. So the impulse response is given as differential output variable with respect to time. And notice that we had equation 2 previously having the same differential output variable with respect to time. However, this is a step response, and now we're talking about an impulse response. So the impulse response is given as c over tau times exponential raised to the power t over tau. And then recall that the impulse is denoted as c. Going back to figure 5.2, we have a balance. So we have component material balance, we have energy balance, overall material balance, we have a current balance, which is physics, and then we have a force balance, which is also physics. We have the input, the output, the proportional gain, and the time constant. So this is for a first order process. We're given variables such as concentration, we're given the proportional gain, we're given the time constant, we're given the temperatures, we're given the flows, and neglecting the current and force balances because I don't think we're talking about it. Moving on, we'll go to the first order system. The amplitude ratio is never greater than the process gain, and it decreases monotonically as the frequency increases. We have the amplitude ratio is equation 5.4, it's denoted as AR. It's equal to the transfer function with respect to variables j and w, and it's the absolute value of the transfer function. Thus, this will just mean that we have the absolute value of the output variable with respect to j and w over the absolute value of the input variable with respect to j and w. And then here we end up saying that it's just kp over the square root of 1 plus w squared plus tau squared. If we take a look at equation 5.1, we were given the transfer function in terms of Laplace domain, and once we switch the Laplace domain's variable s to equal j times w, we turned it into equation 5.4. But notice, there is no j, there's just w. And also notice that it has a square in the denominator, but it also has an encompassing square root of that square. These are just amplitude ratio fundamental principles. This is the function you're supposed to use for a first order system. Concerning a second order system is identified by a second order derivative. So it occurs when two first order or one second order ordinary differential equation is required to model the dynamic behavior. Some examples are given in figure 5.3, and also the transfer function for a second order system with a gain in the numerator can be written as equation 5.5. For equation 5.5, the differences between first order and second order system is namely that we have a second order derivative, and also we have the introduction of a damping factor titled t. Also, we are given the transfer function. It's different for a first and second order system. And lastly, we're given a new variable titled alpha, and alpha is the two roots of the characteristic polynomial. Thus, the formula for alpha is simply the quadratic formula. Concerning figure 5.3 and 5.2, these are descriptions of first order and second order systems. The differences between these are namely in the proportional gain and the time constant. Additionally, there is another column presented in figure 5.3. It's the dampening factor times the time constant. So the differences between the two orders of the systems, first and second order systems, for the proportional gain we have the same denominator, but the numerator is different in so fact that the numerator is vk versus f, and then the time constant is just different. Time constant has a v over f times vk. For a second order system, it's tau a times tau b. So as I was saying, the parameter t is termed the dampening factor, and alpha are the two roots of the characteristic polynomial, and they depend on exponents of the time domain output function. When the dampening coefficient is less than 1, the system is termed underdamped. The roots of the characteristic polynomial are complex, and the system will have a periodic behavior for a non-periodic output. For example, the non-isothermal reactor system in section 3.6, which exhibits oscillations for a step input, has a dampening coefficient of 0.15. And when the dampening coefficient is greater than 1, the system is termed overdamped, and the roots of the characteristic polynomial are real. And the system will have a non-periodic response to non-periodic inputs. Finally, the series reactor system in example 3.3 has a dampening coefficient of 1, which indicates real repeated roots, and this type of system is termed critically damped. Two entries are given in figure 5.1 for a second order system. One is for an overdamped system, and the other is for an underdamped. The step response for the overdamped system initially at steady state is monotonic with an initial slope of 0 and an inflection point. Note that the underdamped system experiences periodic behavior even for this simple input. So we have equation 5.6 is the overdamped step response relating to t is greater than 1. So we're given the output variable as a function of the proportional gain. The input variable is also a function of the time constant and time. Next we have equation 5.7, it's the critically damped step response. This is where t is equal to 0. And likewise we have the output variable y as a function of the same variables as equation 5.6. Next we have equation 5.8, it's termed underdamped step response, correlating to a t dampening factor coefficient of less than 1. And then here we have the output variable as a function of the proportional gain, the input variable, t, the time constant, as well as Greek letter phi. This is an introduction to Greek letter phi. Greek letter phi is given as the inverse tangent of ratio square root 1 minus the square of t over t. Moving on, we have equation 5.9, and this is termed overdamped impulse response. So we have the overdamped step response, then we have the overdamped impulse response. And previously in the introduction of this chapter, we defined what a step response and an impulse response was. So again, for the overdamped impulse response, we're given a function for the output variable, which is equal to a function of variables c, which is the impulse, function of t, and tau. Moving on for equation 5.10, it's the critically damped impulse response. This is equation 5.10. And lastly, we have the underdamped impulse response. If you're having trouble learning what impulse and step responses are, they were introduced in the beginning of this chapter. So both the step and impulse responses for a second order system have initial responses that are more gradual than for a first order system. The overdamped system approaches its final value smoothly, while the underdamped system experiences oscillations. The amplitude ratio for the frequency response is monotonically decreasing for an overdamped system and begins to deviate substantially from the proportional gain around the frequency equal to the inverse of the time constant. The amplitude ratio for a second order system with a dampening coefficient below 0.707 exceeds the proportional gain over a limited frequency range around 1 over the time constant. And this resonance effect results from the inherent oscillatory tendency of the system, reinforcing the input sign oscillations. So again, the amplitude ratio is given as equation 5.12 for a second order system. It's also defined similarly the absolute value of the transfer function of variables j and w. And we'll have another note. We no longer have just swapping out s equals j, w. Moreover, it's only w is given for the amplitude ratio, but for a second order system, w and the damping ratio are given. Next up is the dead time. The dead time or transportation delay was introduced in example 4.3 for plug flow of liquids, and it can also occur for transportation of solids along a conveyor belt. It was shown to have the following model, equation 5.13, in which we have the output as a function of t is equal to the input times 1 minus theta. We're also given the transfer function for the dead time. This is in the Laplace domain, so the transfer function is always the output over the input, and this would be equal to e to the power negative theta times s. The step response, the impulse response, and amplitude ratio can all be easily determined because the output is the input translated in time by theta. For example, this leads to the conclusion that the amplitude ratio is equal to 1 for all frequencies, which can be demonstrated mathematically by equation 5.14. Here we have the amplitude ratio. The amplitude ratio in this case is equal to not the transfer function. Well, actually, yes, it is given as the transfer function, and the transfer function is written as the absolute value of e raised to the power jw times theta. Remember, we substitute s equals jw, and this in fact is equal to 1, and then 1 is equal to the absolute value of cosine of w times theta minus j times sine of w times theta. And the dead time can be approximated by a transfer function that replaces the exponential in the Laplace variable with a ratio of polynomials in s. This approach is referred to as a Patti approximation, which is represented and presented in appendix D. In this book, we will not use dead time approximations. We will model the dead time as an exact delay, as given in equation 5.13. So we're not going to use approximations. The importance of dead time to feedback control can be understood by considering an example, such as steering an automobile. With dead time, the automobile would not respond immediately after the change in steering wheel position. Clearly, such an automobile would be difficult to drive and would require a skilled and patient driver who could wait for the effect of the steering wheel change to occur. Next up, we have the integrator. The integrator is a special type of first order system. A process example of an integrator is a level system, which is modeled based on an overall material balance. To give equation 5.15, we have the overall material balance. And in many cases, the inlet and outlet flows do not depend on the level. When no causal relationship exists from the level to the flow, the model has the following general form. Equation 5.16, tau h times d of differential output variable with respect to t is equal to differential input variable, and this is not equal to a function of the differential output variable. Notice that I introduced tau h, and this is the hold-up time. Also, we're given equation 5.17. This is the transfer function. The transfer function is simply equal to the inverse of the hold-up time times s. The important difference between the integrator and the first order system in equation 5.1 is the lack of dependence of the derivative of the output variable. The output variable being y differential, and that means that the derivative of the differential output variable with respect to t is independent of the output variable differential. So this results in a pole of s equals 0 in the transfer function. The analytical expression for the output of the integrator is given by equation 5.18, in which fact we're saying that the output differential with respect to t is equal to the integral from 0 to t of the integrand differential input variable with respect to differential time domain, and that's multiplied by d differential t. A system like this simply accumulates the net input less the name integrator. If the deviation in the input remains non-zero and of the same sign, the magnitude of the idealized model output increases without limit as time increases towards infinity. For a step response, we have equation 5.19, given the differential of the output variable is equal to the change of the input variable divided by the hold-up time and times t. The impulse response also demonstrates that the system integrates the impulse, so this is the area under the impulse function, and then the output variable remains constant at its altered value when the differential of the input variable with respect to t returns to 0. The value of the impulse response is the differential of the output is equal to c, the impulse, over the hold-up time, and then the amplitude ratio can be determined by equation 5.20. So this is in the section integrator. The frequency response is given as the amplitude ratio, and remember the amplitude ratio is equal to the absolute value of the transfer function with respect to variables j and w, and then we would end up just saying, taking equation 5.17, taking the absolute value of that. We have some manipulation of this. We end up saying that 1 over the hold-up time times j times w is equal to 1 over the hold-up time times w. Most of the time, the j just cancels out, and in fact, what we're doing, we end up multiplying by w times j in the numerator, and then we have the w squared in the denominator. I'm not sure what the math even is. This is the results, equation 5.20. As the frequency decreases, the amount accumulated by the integrator each half period increases. Next, we have the self-regulation. The unique behavior of the integrator demonstrates that not all processes tend to a steady state after input changes cease, and all inputs are constant. To clarify the distinction, the term self-regulation is introduced here. For a process that is self-regulatory, the output variables tend to a steady state after the input variables have reached constant values. Many processes encountered to this point have been self-regulatory, including the chemical reactors, the heat exchangers, and mix and takes. Self-regulatory processes are generally easier to operate because they tend to a steady state. Naturally, the final steady state might be acceptable or not depending on the magnitude and direction of the input changes, so that process control is often applied to self-regulatory processes. The self-regulation of a process can be identified by analyzing the dynamic model to determine if the value of the output variable influences its derivative. For example, the heat exchanger example 3.7 has inherent negative feedback because an increase in the output temperature causes a decrease in a model input term. Here we have negative F over V plus UA over V rho Cp, and all of that is multiplied by T. So this stabilizes the system by decreasing the derivative dt over dt, equation 5.21, and we have all this math for the self-regulation process. And note that some processes have inherent positive and negative feedback. For example, the non-isothermal chemical reactor with exothermic chemical reaction is given by equation 5.22. This is similar to equation 5.21, except for the fact that we have an extra term titled the inherent positive feedback. Here we have the heat of reaction. We also have a K value, we have RT. Moving on, the reactor has a negative feedback term in its energy balance, the same as for the heat exchanger. However, the exothermic chemical reaction contributes positive feedback because the input term, the inherent positive feedback, increases when the output temperature increases. For the parameter values in table C1, case 1, the inherent negative feedback in process dominates, and the process achieves a steady state after a step input. The positive feedback is substantial, however, and it leads to the periodic behavior and complex poles. Additional comments on the behavior and stability of processes are given in Appendix C. In contrast, non-self-regulatory processes do not tend to steady state operation after all inputs have reached constant values. Thus, even a small and constant input change from initial steady state can lead to large disturbances after a long time. A non-regulatory process can be identified from its dynamic model. The value of the output variable does not influence its derivative as shown in equation 5.15. Equation 5.15 is under the section integrator, and now we're in section self-regulation. So, its derivative as shown in equation 5.15, so that the derivative can have a constant, non-zero value over a long time. Without intervention, a non-self-regulatory process can experience very large deviation from desired values. Therefore, all non-self-regulatory processes require process control. The dynamics of typical non-self-regulatory processes are covered in chapter 18, along with control technology tailored to their special requirements. In summary, many different systems obeying the model of these basic elements behave in a similar manner. After the parameters have been determined, the behavior for specific inputs is well understood, thus the experience learned from a few examples can be extended with care to many other systems.